for the duration of the lecture. We encourage you all to ask questions during the lecture, but please do so in the chat. One of the organizers will communicate your questions to the instructor. You will also have an opportunity to ask questions verbally at the end of each lecture. With that being said, we're very excited to have Sahana Balasubramanya, who's speaking about acylindrically and relatively hyperbolic groups. Take it away, Sahana.
Thanks, Macarena. So today's topic that I'm going to be talking about are hyperbolically embedded subgroups. And these turn out to be one of the really important tools when studying acylindrically hyperbolic groups. And for most of this talk, I'm actually going to be focusing on Cayley graphs of a group because the definition of hyperbolically embedded subgroup goes through a very particular Cayley graph. And so just to remind you all, if you have a group G and you have a set S, which is a generating set, and I do not assume that this is finite, so this could be an infinite generating set. And the notion of an infinite generating set is sort of analogous to a finite one. Every group element still has some finite representation in the elements of this generating set. But associated to this information, you can always draw the Cayley graph of your group. And what is this graph? Well, it's a graph whose vertex set is the elements of G. And what is the edge set? Well, the edge set is given by the following rule. If you have G and you have an element S in your generating set, then the oriented edge, which is labeled by S, maps G to GS. Okay? And the reason we follow this convention is because this is what is compatible with the left isometric action of your group. So if you act isometrically by G inverse on the left in this picture, what you're going to get is that the identity is attached by S to the element S. And the reason that this is an oriented edge is because when you read labels in your Cayley graph, which I'll also talk about in slightly more detail in a second, when you move from left to right across this edge, because this is consistent with the orientation of this edge, I will read this as an S. But if I were to move in the reverse direction across this edge, I will read that as an S inverse. So that's why my edges always have a certain orientation. And in this Cayley graph, if you have 2 points, X and Y, and there's some path between them, so this is some sequence of edges, and let's call these edges E1, E2, En, then the label of this path P is me just reading what exactly are the labels of these edges. So the label of this path will be E1, E2, up until En. And this is true for any general path. And naturally, if you want P to be a geodesic path between X and Y, then this N is going to be the minimum number that's possible, right? So this is a graph with a combinatorial metric on it where you just count the number of edges between 2 points to understand their distance. Okay, but with this convention set up and with the understanding that now not only am I talking about isometric actions, but left isometric actions, so that whenever I read letters in my generating set, those will get attached to the right, because those are the two conventions that are compatible with each other, I can begin to work on the setup for hyperbolically embedded subgroups. So what is the setup we need? So let G be a group. And let X be a subset of G, which again is not necessarily finite. And suppose that we have this collection of subgroups which are indexed by some indexing set I. So I make no claims about whether this is even countable or uncountable. It's just some indexing collection. So suppose that this is a collection of subgroups of G such that the following is true. The group G is generated by X union all of these subgroups that I have. Okay? In this setting, I'm going to term this set X and call it a relative generating set. And the reason we call it a relative generating set is because X generates G relative to this collection of subgroups. Okay? So we have this setup, and what am I going to do? I'm going to consider a space which is almost the calligraph of G with respect to this generating set, X union the collection of all the subgroups, but I'm going to make one slight modification to my ed set. Here's what I'm going to do. I'm going to consider the space, and I'm going to call it the calligraph of G, because it does turn out to be a calligraph, but my ed set isn't just the union. I will consider this to be the disjoint union of X along with all of the subgroups that I have in this collection. And what difference does this make? Well, you see, if I were to just construct the calligraph following this rule that's given over here, then my element S, which belongs to my generating set, right, this doesn't really provide me with information about whether the element S is in the relative generating set X or whether it's in one of my subgroups H. So when I put this disjoint union over here, the reason that this disjoint union is here is because it symbolizes a disjoint set of alphabets. For the edges. And what does that mean? It means that I think of all the elements that belong to X as having one particular color. And for every lambda, I think of all of the elements of H lambda as having one particular color. And in this space, what am I going to do? If I have an element S that belongs to, say, X, and it also belongs to H lambda, then in the space, I do the following. I have the identity and I have S. And let's assume that I specify that the orange color denotes all the elements of X and the purple denotes all of the elements of H lambda. Well, in this space, I'm going to have two edges. I'm going to have one edge that is labeled by S, but it comes with the purple coloring to symbolize that this is where I think of it as an element of H lambda. And I'm also going to have an orange edge, which is also labeled by the same element S, but this is where I think of it as being an element of this relative calligraph. And similarly, if I say had a third lambda, H lambda prime to which this S belongs, I would similarly have this third edge, which comes with its blue coloring to denote the inclusion into H lambda prime, which also gives me one more edge here between 1 and S. So this is not quite the calligraph as we're used to thinking about it, but it's very close to being that calligraph. In fact, it's just a slightly puffier version of this normal calligraph. But I have more edges with more colors, which allow me to distinguish between where I think of these elements as living. So I think of this element as belonging to X, this one belongs to the H lambda prime, and this one belongs to H lambda. And there's one edge for each of those.
If I understand correctly, this does not change the distance at all, right?
Correct. This does not change the distance at all. It just gives you more than, definitely gives you more than one geodesic. But that's okay.
Thank you.
Sure. So now, why am I trying to do this? You'll understand that in just a few minutes. But in this setting, what I have is this complete subgraph, which embeds into my bigger space. And how do I think of this embedding? I think of this embedding in the following way, that let's suppose the color associated to H lambda is the green set of edges, then in my actual space, where this is the larger space, I have a set of vertices, which are the vertices of H lambda, my subgroup. But more importantly, I have the green edges that provide direct connections between these elements, because every element of H lambda is an element of my generating set. So this sits as a complete subgraph in my ambient space. And the other reason I'm writing it this way is because I'm not just concerned with all of the edges that have this green coloring, right? Because if this is gamma H lambda, then for every G in G, which defines a coset and a left coset of this subgroup, I will have an isometric copy of this subgroup sitting there, right? And I'll have an isometric copy of this exact subgraph sitting over here. But I don't want to be concerned with the cosets. I only want to be concerned with the subgroup. And that's why I write it this way, to tell you that I'm concerned about the vertex set that corresponds to the subgroup and the set of edges that live inside that specific subgraph. So I'm concerned with this subgraph and not with this one. Okay, so in this setting, with this understanding of this embedding of a subgraph, I can define a very special kind of path that I'm interested in. So here is the definition. Let X and Y belong to one of your subgroups in your collection. A path P in our ambient space between X and Y is said to be admissible if P contains no edges from this particular complete subgraph. Okay, and now you'll see why I wrote it this way, because you might wonder that I could have said it as it contains no edges with the labeling from H lambda, but that's not what I mean. What I mean is that if I have my ambient space, and here is my complete subgraph, and let's say here are my 2 points X and Y. What I mean by an admissible path is a path that looks like the following, that it leaves this space, perhaps has a different set of edges of different colors, meanders about in the space, and then it comes back to this point Y. However, the only thing that I want to avoid in this scenario are the edges that are specifically in this subgraph. And what does that mean? It means that if, say, there is a copy of the coset of this complete subgraph, I am actually allowed to do the following. I am actually allowed to get into the space to pick up one of these green edges and then perhaps meander about and come back to this point Y. Okay, so I'm allowed to pick up these edges that come from the cosets, but the only green edges that I wish to avoid are the ones that are embedded over here. And that's why this path should just avoid the edges from here. But that doesn't mean that you can't pick up other edges that have a labeling from this particular subgroup, because you are allowed to pick up the edges from a coset, which will of course come with the same coloring. Okay. But what are we trying to do with these admissible paths? We're trying to build a very special metric on our subgroups. So here is the definition of what is the relative metric. So I'm going to define this metric, and I'm going to define it for every subgroup in my collection, and hence I have this little subscript lambda. And what does my metric look like? Well, if we let X and Y belong to our subgroup, then this metric has the following form. It is going to be the length of the shortest admissible path between X and Y in our ambient space, provided, of course, that it exists. Because it is not guaranteed that for any 2 points in our subgroup, I would have such an admissible path. And if it doesn't exist, I set the metric to be plus infinity. Okay. And now to convince you that this is indeed a metric on your subgroup, let's quickly check that. So here's our ambient space. And here's my complete subgraph. And I have 2 points X and Y in here. And the first thing that, of course, we want to check is that if X equals Y, then the length of this admissible path is 0. And remember, this length is in terms of the number of edges. It is the combinatorial metric on this graph. So let me perhaps annotate that this is the number of edges. And so if X and Y are the same point, well, I don't need to move anywhere, because I don't need to pick up any sort of edges in order to stay at the same place. And so, of course, this is 0 always. And conversely, if this relative metric takes the value 0, then it implies that X equals Y, because what this is telling you is that you did not take any edge in order to go from X to Y, and therefore you stayed at the same place, and therefore X must equal Y. It satisfies symmetry naturally, because if you have some admissible path in this Cayley graph, that goes between X and Y, then of course I can read the labeling of this path in one direction in order to achieve a path from X to Y. But if I read the labeling in the reverse order with the reverse orientation, I will get an admissible path from Y to X. So of course, if there is an admissible path that goes from X to Y, there is also an admissible path from Y to X. And the distance, the one that has the minimum length is, of course, the one that has the minimum length in reverse. And so this is also true, which is the symmetric property required by a metric. And lastly, the triangle inequality. Well, let me extend my space a bit more so that I have a bit more space. And let's say you have another point Z, and you have an admissible path between Y and Z. then you can simply see that if alpha was the admissible path that ran between x and y, and beta was the admissible path that ran between y and z, then the concatenation of these two paths, alpha and beta, provides an admissible path between x and z. And you're allowed to touch the vertices of this subgraph. You're just not allowed to pick up the edges. And of course, this concatenated path does not pick up any edges from this complete subgraph still. And therefore, you have the triangle inequality. Which is the last requirement for this function to be a metric. And so all these three things combined tell you that this is indeed a metric on your subgroup. But now that you have a metric on your subgroup, you can actually extend this to the whole group. So we extend simply by taking that the distance between the 2 points is, and I'm going to abuse notation here slightly, that this is this, provided x inverse y belongs to h lambda. And what does this condition do? What it does is extend the metric from the subgroup to all of its left cosets. And instead, you set it to be plus infinity otherwise. Which means that if x inverse y does not belong to the designated subgroup, then the admissible length is always plus infinity. Okay, so that was a lot of information, but we're finally ready to be able to define what is, in fact, a hyperbolically embedded subgroup. And I'm going to abbreviate it as H dot E dot for future reference. So let X be a subset of G and a collection of subgroups of G, such that, of course, G is generated by this union. We say that our collection of subgroups is hyperbolically embedded in G with respect to X. And now you see the dependency on this relative generating set turning up in our setup if the following two conditions are true. The first condition is that our space that we were considering for so long, this should be a hyperbolic space with the usual word metric on it, which is associated to this generating set. But moreover, I want some sort of properness condition on my subgroups, and that was the reason for defining these relative metrics. So I request that the relative metric is locally finite for every index that I have. And what does this mean? It means that every ball of finite radius in this relative metric has finite cardinality. And notice that I do not request that the cardinality of the ball needs to be uniformly controlled or anything like that. No, if you change the radius or if you consider balls of the same radius in different parts of the space, this cardinality may very well change. But as long as it's still finite, that's all that I care about. And what is the notation that we use to denote this phenomenon? We're going to use the following notation. We use the embedded symbol with the subscript H, into the pair G and X, because of course this definition depends on the choice of this relative generating set X. And more generally, we say that this collection is hyperbolically embedded in G if you can find an X that satisfies the definition of being hyperbolically embedded for some subset X of G, which again does not need to be finite. Okay, so as long as you can find some relative generating set X that satisfies these two conditions, H, or rather the collection of subgroups, is going to be hyperbolically embedded into G. Okay, this is a complicated definition. It's also rather long. Let's see some examples which hopefully build our understanding. Okay, so the first example that I'm going to do is sort of the trivial example. This is sort of the stupidest thing that you could do. I'm going to set X to be the empty set, and I'm going to take the subgroup H to be the complete group G. And then, of course, it is easy to see that G hyperbolically embeds into G with respect to itself, right? And why is that? Well, because of the way I've set this up, when I consider my Cayley graph, this is going to be a completely bounded space of diameter 1. Because, of course, every element of G is part of your generating set, and between any two elements of G, there's exactly an edge between them, which is labeled by the difference of those two elements, which is still an element of G. But why is this hyperbolically embedded? It's because I've kept my relative generating set empty. So now if I have 2 points, X and Y, in my space, and I want to get across from one to the other using an admissible path, it's impossible for me to do, because every edge in this graph is an element of my designated subgroup, and there are no admissible paths in this Cayley graph. So because there are no admissible paths, what that tells me is that the relative metric between any two elements is going to be plus infinity for all G1 that are not equal to G2. And in particular, if I consider the ball in this relative metric around any element of any finite radius, well, this is going to have cardinality exactly 1. And so for this very degenerate reason, you get that G is always hyperbolically embedded into itself with respect to the generating set that is the entire group. And it is for this reason that when we actually deal with hyperbolically embedded subgroups in some way that actually makes sense, we always talk about proper hyperbolically embedded subgroups. So this notion is really useful when you've got a proper subgroup H and a proper subset X of G that actually satisfies this definition. Is there a question? Okay, I saw something flash on my screen, and I was concerned that there might have been a question.
There was just a question. I mean, it should. I mean, you say G embeds in G comma empty set union G, but it should just be the empty set, right?
Yeah, just be the empty set. Yeah, that's where you put your relative generating set. Yeah, thank you.
Thanks.
Yes. Okay. So that's a trivial example, but let's look at an example that isn't so trivial. So I'm going to allow my group to have the structure of H direct product with the infinite cyclic group Z. And I'm going to specify that the generator of my infinite cyclic group is the letter T. And so what am I going to do? I'm going to set the relative generating set to be the singleton T and T inverse. And I'm going to take H, my designated subgroup, to be exactly the H that's popping up here, okay? And so I'm trying to understand what is the Cayley graph of my group with respect to the generating set H, disjoint union, T, and T inverse. And I think we can all agree pretty quickly that, of course, this acts as a generating set for my group. So what does this Cayley graph look like? Well, it actually looks like a quasi-line, which is therefore a hyperbolic space. So what you end up having is the complete subgraph on H, which of course is a bounded set of diameter 1. But then from every vertex in this subgraph, I have an edge, which is marked by T, which moves out of this space. And I also have an incoming edge T into every vertex of this space. And where do these T edges go and attach to? Well, they go and attach to a copy of my subgroup, which actually is represented by the coset TH. And so over here, I have these vertices, and I again have a complete subgraph on them. And similarly, the incoming T edges are actually coming from the coset represented by T inverse H. So there's a vertex again for every element in the coset, and you have a complete subgraph on this. And then this picture just keeps going ad infinitum, right? Again, you have an outgoing edge T from every element over here. And over here, you have an incoming edge T from every element. And as you might expect, the next coset that you're going to run into is T squared of H, which again has a complete subgraph on it. And now you just keep going. And similarly over here, you have a complete subgraph on T to the minus 2H. And then you just keep going, right, with the corresponding edges moving out. So this is what your Cayley graph looks like. And this is very much hyperbolic because this is a quasi-line. It is quasi-isometric to a line, and hence it is hyperbolic because we know hyperbolicity is preserved by quasi-isometries, and a line is, of course, zero hyperbolic. And then the question comes, okay, we have the first condition of our definition being satisfied. Can we check whether the relative metric is indeed locally finite? And here's what's happening in this example. Supposing this is my X and this is my Y. These are the 2 points in my subgroup. And I'm interested in understanding what's an admissible path between them. Well, what can I do? What I can do is the following. I can leave this subgraph using my T edge. I can take an edge which is directly marked by an edge in this complete subgraph. And even though its labeling comes from this subgroup, it does not belong to this subgraph. And then I can come back down using a T inverse. And that is, in fact, going to be an admissible path in this space. But what does that mean? What that means is that if I consider the ball centered around the identity, which of course is an element of my subgroup, just of radius, let me call the identity E, and I consider the ball of radius 3 in this admissible path, well, its cardinality, because of this argument, is actually going to equal the cardinality of H. And what that means is that if the cardinality of H is infinite, then H does not hyperbolically embed into my group G with respect to this specific X that I had. which of course, as you may remember, was T and T inverse. Right, so that means direct products are kind of bad for having hyperbolically embedded subgroups, especially if one of your groups is infinite. This is what this example is telling you. And this is also why it is true, this is a theorem that I will just mention as an aside, that if you have a group that looks like a direct product of two groups, where A and B are both infinite, then actually G is not acylindrically hyperbolic. So this is somehow tied into the structure of acylindrically hyperbolic groups, which can never split as direct products. And that's why when we talk about rags being acylindrically hyperbolic, or even fundamental graphs of groups being acylindrically hyperbolic, there's always this proviso that they should be not directly decomposable, which means that they don't split as this direct product. Okay, but what's an example of something that is hyperbolically embedded? Well, that's going to be example 3. And at one end of the spectrum, if you have direct products, at the other end of the spectrum, you have free products. So I'm going to take G to be equal to H, free product with Z, where again, I let the generator of Z be the letter T. And again, I set my X to be equal to T and T inverse, and I choose the subgroup H, which is exactly the subgroup in this free product. And once again, I am interested in what this Cayley graph looks like. And in this case, it turns out that the Cayley graph is also hyperbolic, and it turns out to be a quasi-tree. So what's going on over here? Because of the free product structure, you have the complete subgraph on H. And then from every vertex of this space, I have a T edge that leaves and that is incoming. But every one of these T edges maps to a fresh copy of this subgroup, which don't overlap with each other. So when I've branched out of T because of the free product structure, I have another copy of the subgroup here. I have another copy of this complete subgraph over here. And all of these are, of course, defined by different cosets of the group. And the same is true for the incoming edges with respect to T. And now this picture keeps going. Every vertex here has an outgoing edge. You have lots of incoming edges. And so on and so forth, right? And this is not a true tree. And the reason is because, your vertices are thickened spaces, although they're bounded in diameter. But this structure does lend itself to making this space a quasi-tree. So it's quasi-isometric to a tree, which is still quasi-isometric to a hyperbolic space and is therefore still hyperbolic. So again, we have that our first condition, our first criterion for being hyperbolically embedded has been satisfied. What about that second condition on the relative metric? Let's check. So let's pick X to be here and Y to be here. And now I want an admissible path in this space, which gets me from X to Y. And that means that I'm not allowed to take any of the edges from this specific subgraph. So what am I forced to do? I'm forced to leave by one of these T edges, and then I have to sort of meander around in the space. But remember, this looks like a quasi-tree. There's no way for me to somehow loop back into this space and come down one of these paths and get to Y. There's just no way for me to do that because this is a quasi-tree. And therefore, the only thing that I can do is if I leave via one of these T edges, at some point in time, I have to turn back onto myself and come back the way I went, but then I'm exactly at the place where I started, and I can't pick this edge up to go across. So what this is telling me is that the relative metric between x and y, this relative distance, is always going to be plus infinity if x does not equal y. And therefore, if you consider the ball centered around the identity with respect to any finite radius, this always has cardinality 1. And therefore, you get that h is hyperbolically embedded into G with respect to our choice of x. And this is always the case, irrespective of what cardinality h has. Okay, so we've defined this notion, we've seen some examples, and now the big question is, what does this have to do with acylindrically hyperbolic groups? And the answer is given by this theorem of Denis Osin, and the answer is it has everything to do with the class of acylindrically hyperbolic groups. So theorem due to Osin, and I'll give you the statement and then I'll convince you of why this theorem is true. The following are equivalent. So the first condition is that G is acylindrically hyperbolic. And remember, what that means is that G admits a non-elementary acylindrical action on a hyperbolic space. The second criterion is that G has an infinite non-degenerate proper hyperbolically embedded subgroup. So the presence of these infinite proper hyperbolically embedded subgroups is an immediate marker of acylindrical hyperbolicity. And then the third condition is that there exists a generating set, which is again not necessarily finite, A of G, such that if you draw the genuine Cayley graph of your group G with respect to this set A, then this is hyperbolic. And the G action on this Cayley graph is non-elementary and acylindrical. So you see the power of this theorem. You've gone from requesting that you have an action which is non-elementary and acylindrical on some hyperbolic space to actually having such an action on a Cayley graph, which is additionally co-bounded. So that's stronger than a general action. And why are these conditions equivalent? Well, first of all, I think we would all agree that if I had the third condition to start with, then of course this automatically implies 1. So 3 implies 1 is sort of obvious from the definition, because of course this is an acylindrical non-elementary action on some hyperbolic space. How do we get from 1 to 2? Well, it turns out this has everything to do with loxodromic elements. So if your group G is acylindrically hyperbolic, remember you have lots and lots of independent loxodromics. And if G is a loxodromic element associated to this action on the hyperbolic space that satisfies the definition of being acylindrically hyperbolic, then associated to this loxodromic element, you have what is known as the elementary subgroup associated to G. And it turns out that E of G is virtually cyclic, and that E of G always hyperbolically embeds into your group G. And so in very specific examples, this gives you subgroups associated to very particular types of elements. So for example, if your group was the mapping class group, the loxodromics in that case are the pseudo-anisods acting on the surface. And so their elementary subgroups are virtually cyclic and hyperbolically embed into G.
Did you define what it means to be elementary cyclic, or you?
No.
Sorry, like elementary subgroup.
No, I haven't defined what it is, but if you want to know what it is, so associated to this loxodromic element, you have this quasi-geodesic axis in your space along which your group element acts. And what you do is you take the stabilizers of the endpoints of infinity of this quasi-geodesic. So this quasi-geodesic defines a G plus infinity and a G minus infinity. And the elementary subgroup is all the elements of the group that stabilize these G plus or minus infinity. The other way to think about it is that these are all the elements of the group that take this bi-infinite quasi-geodesic axis and push it at most finite Hausdorff distance away. And it turns out to be, because of the acylindricity, it is virtually cyclic and it hyperbolically embeds. Okay, and why does 2 imply 3? Well, our hyperbolically embedded subgroup is giving us a candidate Cayley graph, right? Whenever we talk about this hyperbolically embedded subgroup, we know that we have some Cayley graph that looks like this. And let me say this is the hyperbolically embedded subgroup H, right? And we already know that this is hyperbolic by definition. What's the issue? The issue is that we don't know whether the action of the group on this space, even though it's a well-defined action, is acylindrical. But what Denis Osin managed to do is that you can produce a Y which contains your relative generating subset X. And then this is enlarged in a way that if you consider this new Cayley graph, this is still hyperbolic and the G action is acylindrical. So how do you produce this larger Y? Well, what this larger Y is doing is that it's basically crushing things that are close together in your space so that you only end up considering things that are far enough. That is what essentially acylindricity cares about. And the way you crush things that are close is that you crush things that don't satisfy some sort of bounded coset penetration property. And you make sure for things that are far away enough, you do satisfy this bounded coset penetration property. And that is exactly what turns it into an acylindrical action. But that is exactly what gives you this Cayley graph on which you have then this nice desired action. But what does this theorem also tell us? It tells us that in view of this second point of this theorem, that having an infinite proper hyperbolically embedded subgroup is a marker of acylindrical hyperbolicity. And this last example 3 that I just ran through, it means that there are very easy ways to construct lots and lots of examples of acylindrically hyperbolic groups. And this is where you start to see the divergence with the behavior from the class of hyperbolic and relatively hyperbolic groups. For example, I think we know that all hyperbolic groups have solvable conjugacy and word problems. But using this example, by taking a free product with Z, you could actually construct an example of something that is acylindrically hyperbolic, because H would function as this infinite proper hyperbolically embedded subgroup. But you could choose your H in a way that violates having a solvable conjugacy or a solvable word problem. So this example really allows you to build lots of examples for acylindrically hyperbolic groups that could have extremely strange, extremely diverse properties. But what's really nice about hyperbolically embedded subgroups is that they are actually related to the notion of peripheral subgroups for relatively hyperbolic groups. And if you remember my lecture from yesterday, I spoke briefly about them, and as promised, I'm going to tell you exactly what is the relationship. So this is the theorem, which is again due to Dahmani, Girardel, and Osin. And the reason that I'm going to also state it is because, you know, the notion of hyperbolically embedded subgroups didn't just occur randomly. They took inspiration from the peripheral system for the relatively hyperbolic groups. And it's nice when things come around in full circle and you see that what you've defined is a true generalization of what you started with as inspiration. So the theorem is that G is hyperbolic relative to H, and I'm going to state it for one subgroup, but the same is true for a collection of subgroups. If and only if H hyperbolically embeds into G with respect to X for some finite subset X of G. So in the specific case, when you know that this relative generating set has finite cardinality, then not only are you hyperbolically embedded, but it turns out that the group G is actually hyperbolic relative to H. In other words, H is now a peripheral subgroup and not just a hyperbolically embedded subgroup for G. And you can actually take this to be the definition of relative hyperbolicity if you like, because it is a true generalization of the concept. And you know, these hyperbolically embedded subgroups have been used, like I said, to produce lots of examples for this class of groups. So for example, Sisto used this second part of the theorem to show that groups acting properly on proper cat0 spaces with rank 1 elements are in this class of groups, because what he showed is that the elementary subgroup associated to those rank 1 elements is hyperbolically embedded. And then you may ask, okay, these ones are virtually cyclic. Are they the only hyperbolically embedded subgroups? And the answer is no. There are actually a very rich class of hyperbolically embedded subgroups. So if G is acylindrically hyperbolic, then for every natural number n, there exists a subgroup H of G such that H is, of course, hyperbolically embedded in G, but more importantly, H is isomorphic to the free group of rank n cross K, where K is finite. So we don't just have hyperbolically embedded subgroups that are virtually cyclic. You can actually produce a very large class of hyperbolically embedded subgroups. And this was actually used to show, so what can you use it to show? You can use it to show that the elementary theory of G, which is acylindrically hyperbolic, is not superstable. So it went into showing that. These properties were also used to show that acylindrically hyperbolic groups are SQ universal, that they have unbounded second cohomology. A lot of the theorems that I mentioned in my first lecture were provable because this theory works out the way it does. And the last theorems that I'll tell you with are some combination theorems that I think will be useful for those of you who are interested in those combination type results. And I'll state it in two parts, one for H and N extensions and the other for amalgamated products. Does anyone know what superstable means? Okay, I do know what it means, but what it means is that the elementary theory of the group is not stable under certain types of nice extensions as well. So, okay, so what are these combination theorems that pertain to these acylindrically hyperbolic groups? So suppose you have G, a group, and you have a pair of subgroups that hyperbolically embed into G with, let's say, I from K to H, an isomorphism. Then H still hyperbolically embeds into G prime, where what is G prime? Well, G prime is the H and N extension of G which of course conjugates K onto H. So you can take such an H and N extension and still produce a hyperbolically embedded subgroup. And you can actually do the same for amalgamated products. So if H hyperbolically embeds into A, K hyperbolically embeds into V, and if, of course, H is isomorphic to K, then H equals K hyperbolically embeds into the amalgamated product of A and B, where the amalgamation, of course, is over the isomorphic subgroups H and K. So these notions survive these fundamental ways of building new groups, which are pretty popular in geometric group theory. And that's what makes them a really nice tool to use when you've got groups that maybe are ascending agent and extensions or look like amalgamated products of something else that you might be able to understand more easily. Okay, so I'm going to stop here for today. And tomorrow, when I talk about group theoretic Danes fillings, you'll get to see one more application of hyperbolically embedded subgroups. And that's the reason I didn't mention that application here, so that I can talk about it tomorrow. And hopefully that'll further convince